All right, so I said for commutative, you just have to make sure, or rather, you just have to find the left-hand side, which is given by A star B star C. And you also find the right-hand side, which is given by A star B star C, like this. So this is how you prove for commutative. For this is associative, and then commutative is simply just A star B and then B star A. So commutative, associative. Now let's look at how to find the identity. So I'll give one scenario here. I'll give one scenario, which is just this one here. When you have, for instance, you have 2. So we all know to say the inverse of 2 is simply 1/2. So when you multiply 1 over 2 and 2, the answer that you get is simply just 1. So this one is called an identity element. So this one is called an identity element. And then this number that we're multiplying to this original number, which is a whole number, to get an identity element is called an inverse. So once you multiply an inverse and its, when you multiply an inverse and its original number, the answer that you get is an identity element. So same applies to binary operations. Now let's take this multiplication sign to be just any operation. Let's say, for instance, star. So if we have A star, A star. Okay, first, before I do this, let me also tell you that if you multiply this identity element, if you have the identity element, in this case, the identity element is 1. So when you multiply 1 times 2, the answer you get is simply just 2. So when you multiply this identity element with its just number or with any number, the answer you get is simply just that number. For matrices, if you are multiplying the identity elements for a 2x2 matrix, maybe you have A, B, C, D. If you have something like this, and then if you multiply with its identity, which is just given by this, the answer you get will simply just be A, B, C, D. It will be the same. It will still be the same thing. So even when it comes to binary operations, you still have the same thing. So for instance, you have, so what I was explaining is that if you have a function A a function or a set A, and then this set A, you have an operation there. You make an operation, or rather you just, let's say for instance, this is multiplication. If you have this set A times, or this element in set A times its identity, this is what I was given. The element times its identity gives us the same element. So the element times its identity, if we take that this identity element is E, the answer that we're supposed to get should just be that same element A. Same applies if we switch this. If we switch, we put 2 this side and then we put 1 this side. If we multiply the identity, the element with the identity, the answer will still be the element. So even if we switch these, we say E star A, the answer should still give us A. So for this reason, we use this to find the inverse, because we know to say when you multiply an element with its inverse, the answer will just get, the answer that you just get will simply just be an identity element. Yeah, so what I'm trying to talk about the inverse is that if you have the element A multiplied, rather, or you find an operation of A and its inverse. So I'll write it as A inverse. The answer that you get is simply just E. Or rather, let me say, according to the explanation there, we can say A inverse is simply just B. So when you find A star B, the answer should give us what? Should give us E, because we've defined B to be the inverse of A. So when you find A times its inverse B, the answer should give you an identity element. So this is a very important point that we use to find the identity elements, that we use to find the inverse of any given element. So what again you should understand is that any element that does not have an identity element, it means that it also doesn't have the inverse. So anything, any function, any element that does not have an identity, if it doesn't have E, it means that it also doesn't have the inverse. That's what it means. Yeah, so I don't know if you have questions, maybe we'll proceed. Okay, so there's a question here, a simple question, of course. They're saying star is defined by multiplication, and the set S is equal to the set of integers, which is just ranging from negative infinity to positive infinity. Yeah, so they're asking us to say, is star a binary operation? So is star a binary operation? When we get two integers in this set, we multiply them. Are the answers that we're going to get going to be integers as well? If the answer is yes, then it's a binary operation. So you can try to think of any impossible way, or rather, you can think of maybe any numbers that you may multiply to get something that will not be an integer. Any number, any two integers that we can multiply to get a number that is not an integer. If that exists, it means that it's not a binary operation. But if it doesn't exist, like in this case, there are no numbers that you can multiply to get a number that, there are no integers that you can multiply to get a number that is not an integer. Hence, star is a binary operation. So this one, the answer is yes. Is star commutative? So we know that multiplication is commutative. So even if we can try any two numbers from the set of integers there, so we try two numbers from the set of integers, let's say -2, we multiply it with maybe 0. The answer will be 0. Let's also take 0 times -2. The answer will still be 0. Hence, star is commutative, because after switching, or rather after rearranging the two elements in the function, the answer that we're getting is simply just the same. Okay, so let's move on to associative. So associative, when you talk about associative, remember I said you look at the arrangement of brackets where you say A star B star C should be equal to A star B star C. So you start with the left hand side, you try it. You also go to the right hand side, you try it. So let's pick three numbers from this set. For instance, we can pick maybe any three integers. We can pick 2, and then we also have maybe 3. We also have 2, even 1. Okay, let us now change the arrangement of brackets. So we can start with 2 there, and then we have 3, we have 1. So we can start with the left-hand side, this side. So the left-hand side, we start with what is in the bracket. So 2 star 3, we're using the operation as multiplication there. So 2 star 3 is simply just 2 times 3, which will give us 6. So 2 times 3 is 6, and then we have star 1. So the star there still remains multiplication. So 6 times 1, the answer is 6. Let's see what we're going to get on the right-hand side. So the right-hand side, we have 2 outside, and then we have star. Then in brackets there, we have 3 star 1. which is just the same as 3 times 1. So 3 times 1 is simply just 3. So 2 star 3 is simply just 2 times 3, which will still give us 6. Then since the right hand side is equal to the left hand side, this implies that the given operation is associative on the set of integers. So this operation times, or rather this operation star, is associative on the set of integers. That is what it means. So what I'm just from explaining is what is written here down. Okay, so I've already explained on this, evaluate this, or how to prove for associative using or rather getting 3 numbers from that given set. This is what I'm just from explaining, except that I use different numbers. Okay. So let's look at these tables here. So let S be equal to -1, 0, and 1. So this one is not a set of natural numbers, it's not a set of integers, no. So these are just numbers that have been picked from a certain set. So they are just as they are, like this. We don't have dots at the end this side to show that they are continuing. So the operation has been defined using these 2 tables there. So the question is, determine whether *1, meaning this one, and *2 are binary operations on S. So you just look at the solutions that you found here. If there's any strange number which is not in the set, then it's not a binary operation. Same applies to this part here. So when you look at these numbers that are there, the answers are all just from negative. They are all just -1, 0, and 1, which tells us that star is a binary operation on the set of, on these 2 sets that have been given. So *1 and *2 are binary operations on this set, on set S. So *1 and *2 are binary operation on set S. Why? Because when you look at their solutions, their results here, they are all in the set there. They are all in the set. So if, for instance, we had a 2 there, we would have said *1 is not a binary operation on the set S. Why? Because we have a 2, which is a foreign number. It's not part of the set S. But in this case, when you look at all the numbers, they are all in the set S. All the results that we found, this here and there, they are all in the set S. Hence, *1 and *2 are binary operations on the set of, on the set S that has been given there. And then the question comes in again to say, determine which of the 2 is commutative. So how do you determine that? You look at the solutions that you are getting. So if you find, let's say for instance, 2 numbers which are the same, if you have 2 numbers this side, and you have a number this side and another number, or you can look at maybe 2 operations. Let's take a look at this this table, the first one. So when you look at the first one, you have -1 *0. So you have, let's say, okay, we have -1 *1. The answer is 1. Then we have 0 *1. The answer is -1. So we have 0 *1. The answer is simply just -1. Let us also look at we have 0 *1. 0 *1. The answer is -1 there. Then let's look at -1 *0. So let's look at -1 *0. So -1 *0, -1 *0. So we have this number here, which is just a 0. So since the answers are different here, the reason I've gotten -1 and 1, because I know that they are common. They are common on the, how can I explain this? But okay, let me just say, if you are getting numbers, let me just restart on this one. You don't just pick any number, because you know that there's -1 here, there's -1 there. So if we say -1 *1, and -1 star -1, the answer will still be 1. That one qualifies. Let us now look at 0 star -1. The answer is -1. And then we also look for 0 this side, and then we compare it with the -1, which is on this other side. So we've gotten that 0, and then we say star -1. So 0 star -1, the answer is 0, which implies that star 1 is not commutative. Why? Because we can see that 0 star -1 there, the answer is -1. So 0 star -1, the answer is -1. And then if we say -1 star 0 there, -1 star 0, which is this part, the answer is simply just so -1 star 0, the answer is simply just 0 there. Hence, star 1 is not commutative. So let's look at this one here. There's a question here to say, why is, someone is asking a question to say, why is 0 star -1 not 0? That's what we have been given. These tables have just been given. So the reason why it's not 0 is the reason as to why we're saying it's not commutative. If it was 0, we would have said it was commutative. It would have been commutative in short. But because the answers are different, they are giving us different answers. 0 star -1 and -1 star 0. They are giving different answers, hence not commutative. Let's look at this one. Here we have -1 star 1, which is still giving us -1. Oh, sorry, -1 star -1, the answer is -1. -1 star 0, the answer is 0. Then we have 0 star -1. 0 star -1, the answer is still 0. Okay, let's move on. We have 0 star 1. 0 star 1, the answer is 0. What of 1? What of 1 star 0? So 0 star 1, the answer is, I've seen it. Okay. So 0 star 1, the answer, 0 star 1, the answer is 0. And then what of 1 star 0? 1 star 0. So 1 star 0, the answer is 0. So 1 star 0, the answer is still 0. So when you find 0 star 1 and 1 star 0, the answers are just the same there. It means that the given expression is commutative. So star 2 is commutative. So star 2 is commutative, and then star 1 is not commutative. So it's just as simple as that. You just read the tables. Yeah, so just read the tables, you check the numbers. The reason why I'm picking just specific numbers, when you look at these other numbers like 1 star -1, the answer is -1. -1 star 1, the answer is still -1. All these numbers are just showing us that star 2 is commutative. 0 star -1, the answer is 0. -1 star 0, the answer will still be 0 then. 0 star 0, the answer is 0. Yeah, so that's what it means. Just pick a number that slightly looks different, or you can pick any number. I mean, you can pick any two sets of numbers, but for you to be sure, try to test almost all the numbers in the table. Yeah. Okay. All right, so let's proceed. So I also had to put this very good example at the end. Say the operation star on the set of real numbers is defined by a star b is equal to a squared plus b squared minus 2. Is star a binary operation on the set of real numbers? The answer is yes. Why are we saying yes? It's because whenever you put any real number where there is A and where there is B, the answer that you get will still be a real number. Remember what we defined a real number. We said a real number is simply just a set that is formed when you add rational numbers and irrational numbers. When you add rational numbers and irrational numbers, what you get is simply just a set of real numbers. So in other words, there is no probability of you making this expression undefined, because apart from real numbers, it means that the other number that you can just find outside the set of a real number is just an undefined, something that is undefined. Yeah. Otherwise, real numbers comprises of all the numbers in the world. Any number that you can think of is part of the real numbers. Hence, except imaginary numbers. So if there's no way of you getting an imaginary number after putting your value of A there and your value of B there, it means that the answer that you get, it means that, it means that the star there is a binary operation on R. If there's no way of getting, if there's a way you can get two real numbers, you put them there, and then after putting your real numbers there, you get an answer which is an imaginary number here or undefined, then star wouldn't have been a binary operation. But in this case, whichever real number that you're going to put on A and on B there, the answer that you get there will still be a real number. It will still be part of the set R, or it will still be a member of the set R. So that is how simple it is. So we move on to determining whether star is commutative. So this one you can either use numbers, or if not numbers, you can use letters. So let us use letters. So for commutative, we know that A star B should be equal to B star A. So A star B has already been given in the question, which is just A squared plus B squared minus 2. Now let us find B star A. So B star A is simply just going to be, while there is A there, we put, okay, for simplicity's sake, let me use different letters. I'll use X and Y so that at least you can understand properly. Okay, so let's find X star Y using this expression, which is in terms of A and B. So X star Y will simply just be X squared plus Y squared minus 2. And then if we find Y star X will simply just be Y squared plus X squared minus 2. So X star Y is giving us this, Y star X is giving us that. But this one you can also rearrange it. You can write it as X squared plus Y squared minus 2, which implies that this is equal to this expression. Hence, X star Y is equal to Y star X, which implies that the expression is commutative, or it obeys the commutative law. Let us move on to associative, which is this one. So associative, you can also use numbers or letters. So you can also use numbers or letters for associative. So how do you use letters, or how do you use numbers? So for associative, I showed you how to use numbers. You just get any three numbers in the set of real numbers. Then you test them. That's how you use numbers. So let's use letters. So you have X star Y star Z. Sorry, the bracket is supposed to be. So this should be equal to X star Y star Z for this expression to be associative. So this will simply just now be, so x star y, we put, while there's a, we put x, while there's b, we put y. So we're going to have a squared plus, oh sorry, not a, we're going to have x squared. So we're going to have x squared plus y squared minus 2, and then star z. So what I'm solving is simply just the left-hand side. So the left-hand side is equal to this one. So from there, we can finish it up and say, so this one has become our a, and then our b is z. So while there's a in this expression, we put this, while there's b, we put z. So we're going to have something like this. We're going to have x squared plus y squared minus 2 squared, and then plus z squared minus 2. So this is simply just our x star y star z. Let us now find the right hand side. The right hand side, which is x star y star z. So we start with what is in the brackets. So we have x this side, and then y star z. While there is a, we put y. While there is b, we put z. So we're going to have y squared plus z squared minus 2 then. So from there we can say this one becomes our a, then this whole part becomes our b. So our a will simply just be, so that will be x squared, and then plus y squared plus z squared minus 2, then squared minus 2. So when you look at this expression here, so when you look at this expression here, is it the same as this expression? If they are the same, then it's associative. But if they are different, then it's commutative. Oh, sorry, then it's not associative. So when you look at this expression, the first part here, when we expand this, we expect x to come and have, because at one point we're going to have x squared times x squared, which will give us x to the power 4 on the left-hand side. And then on the right-hand side, when we expand this, we're going to have y to the power 4 instead of x to the power 4. Yeah, even there, we're going to have y to the power 4 at one point. But let us look at z. Let us consider z. Here we only have z to the power 2. But in this case, when you expand this expression, we're going to have, z to the power 4. Here we only have z to the power 2. So this makes these two expressions different. Or if you want, you can talk about x, where you say this x, when expanded, when this expression is expanded, we're going to have x to the power 4 on the left-hand side. But when you look at on the right-hand side, we only have x to the power 2. There's no probability of us having x to the power 4. Hence, these two expressions, this expression and this expression, they are totally different. So if they are different, it means that the left-hand side is not equal to the right-hand side. Hence, not associative, or it does not obey the associative law. So this is the end of binary operations. I'm sure this is not difficult, because I know to say, since the brackets are on 3 and 2, I'm going to start with dealing with 3 and 2. I'll put 3 and 2 in this expression first. So I'll have something like this. I'll have 3, first is 3 star 2, then star 5. So I'll have first 3 squared, because my a is 3, my b is 2, 3 squared plus 2 squared minus 2. Then everything in brackets, then star 5. And then star 5. Then we have star 5 outside. So from there, we can simplify this. Okay, let me just simplify it down there. So this will be 9 plus 4, which is 13 minus 2. This will be 11 star 5. So 11 star 5 is just the same as Our A is 11, B is 5. So this will be 11 squared plus 5 squared, 11 squared plus 5 squared minus 2. So 11 squared is simply just 121. 121 minus, plus 25. Plus 25, you get 146. And then when you subtract 2 there, you get 144. So the answer is simply just 144. This is the answer. So you first have to deal with what is in the brackets there. You first deal with 3 and 2, then you come and put 5 at the end. Right, this is the end of binary operations. So the next time we'll meet, we'll look at complex numbers. Thank you very much for attending tonight's lesson. Okay, Sydney, there's a question? You can ask, please. Sydney, you can ask. Sydney, what was your question?
Hello.
Yes, what was your question, sir?
I wanted to find out why we were squaring the 5 there.
The reason why we're squaring the 5 is...
Yes, on the last point there.
Yeah, it became our B. 11 was our A, and then 5 became our B. We're finding 11 star 5. So meaning while there is A, we put 11, while there is B, we put 5.
Okay, all right.
Yes.
Thank you.
All right, you're most welcome. Okay, so if you don't have questions, we can call it a day. So the next time we're meeting to have, we'll discuss about computer science in the group. And then the next time we meet for mathematics, we'll start complex numbers. And then I'm sending an exercise at the end of this.
So why can't we just agree now while everyone is online?
Okay, so what do you think? What do you want? How do you want us to